Hey there, and welcome back to 2241. This video is going to cover our section 3.2 on partial derivatives, tangent planes, and linear approximations. So first off, our terms. We'll cover the section of a function, partial derivatives, Laplace's equation, harmonic functions, and the wave equation. All of these are related to partial derivatives. And then we will cover the tangent plane, linearization, increments, differentiable functions, and differentials or total differentials. All right, so let's move on to our formulas. In general, we'll have z as a function of x, y, w as a function of x, y, z, and sometimes y as a function of the vector x. Okay, the section of f at y equals b, or at x equals a, is, well, fix one of those values, and then the function that you get, which is a slice of f, we call g, that's the section of f at b. And this is the section of f at a. And we'll have a picture of this on the next page, where you can clearly see that we're slicing out part of the surface f. Let me zoom in a little here. The partial derivative of f at a point AB looks a little complicated, but it is essentially the same idea as the derivative that we've seen before. It's the derivative of f with one of the variables fixed. So we look at these sections and we take their derivatives with respect to the variable that's left over. If you write things in terms of f, this is how they look here. And then this is the notation that we use right here with this sort of curly d, this curly df, curly dx. Usually we just say df, dx, or partial f, partial x. And then some other notation for partial derivatives. We'll have the function with a subscript x, and then the inputs. We'll have partial f, partial x, as we've seen, with the inputs over here. We have z, the output variable, with x written there. And we also have dz dx. And then the last one is capital dxf with the inputs. Okay, and so these are all of the possible partial derivative notations that we might see. We have higher order derivatives as well. We have things like the second derivative, which looks the same. You just take the derivative of the section twice, and you get this. But then we also have mixed partial derivatives, and these we switch to a different section, and it's a section of the partial derivative. So this is a little bit different to interpret. The limit and stuff is the same though, so that doesn't change. All right, what else do we have here? We have Laplace's equation, and that's written this way. Basically, you take this function f, and this triangle operator here means take both second derivatives, no mixed partials, and add them together. And then Laplace's equation says that's equal to 0. Another partial differential equation is the wave equation, where we have u as some function of x, sometimes a vector, and time. So note, Laplace's equation does not have time involved in it, but the wave equation does. It's trying to describe the motion of objects in space. Or actually any periodic motion. That's why we have a time factor here. Okay, and in one dimension, it looks like this. This is what you'll see most of the time. Sometimes in applications, you see the two-dimensional version. If you're doing physics, sometimes you see the three-dimensional version. And then in mathematics, people will often deal with the n-dimensional version of the wave equation because they like to be as general as possible. All right, let's move on to Clairaut's theorem on mixed partials. This guy's French, his name is pronounced Clairaut. And what it says is if both the mixed partial derivatives exist and are continuous, so these functions, not f being continuous, but the derivatives, are continuous in an open ball, we'll talk about this in a second, then fxy ab is equal to fyx ab. So basically, you can do the derivatives in either order as long as these conditions hold, that these guys exist and are continuous in an open ball. This just means if you look at a small region around the point you're interested in, or sorry, the point AB that you're interested in here, then this is true for all points there. Okay, and then you get these mixed partials being equal. Okay. Next up, we have the tangent plane. This is kind of a neat concept. It gets used a lot in differential geometry. The tangent plane to the graph of f at a point is given by this equation. So we have the output variable z equals the value of the function. This just places our tangent plane at the right spot, plus the x derivative at the same point times x minus a, plus the y derivative at the same point times y minus b. So the x minus a and y minus b shift our plane to the right spot, left and right, and or along x, y. And then this FAB shifts our plane to the correct spot along the z-axis. But that still just gives us a horizontal plane. So fx and fy are the things that tell us how to orient the plane so that it matches both tangent lines along the x and y directions at this point. Sometimes I'll notate things this way, or similarly, I'll put like zx or something, zy here, and it'll be understood that we're plugging in this point AB. Okay. I'm going to jump around a little bit because I ordered things a little bit strangely. But we'll cover the increment right now. The increment in a function, or I guess in the output variable z at a point, is given by this formula. So delta z is the difference between the z values at a plus a little bit, b plus a little bit, minus f of ab. So just the difference in z values when you shift a little bit around away from ab. All right, and then the increment kind of goes hand in hand with the total derivative here. And that's why I wrote this. So this is also a delta. It's a lowercase Greek delta. So we have delta z equals the partial derivative of z with respect to x times this delta x plus delta z delta y delta y. Okay, and so these deltas are slightly different from the capital triangle deltas. These are meant to be the change in the tangent plane at a point, not in the graph. So this increment, capital delta z, this is the literal change in z values of the function. But the total derivative and the total differential here measures only the change in the tangent plane at that point. So you find the tangent plane, and then you measure the change in that guy. And so this could be different from capital delta z. Okay, so now let's go on to the differentiability. What does it mean for a function to be C1 in a region U? So it's differentiable at a point in this set U if there exist these two functions, epsilon1 and epsilon2. Oh, and these do not depend on x and y, but on delta x and delta y. That was a slight mistake there. So they depend on delta x and delta y. So if these guys exist so that the increment can also be written in this linear way, right? So we have what looks like the tangent plane almost, plus epsilon1 times delta x plus epsilon2 times delta y. And what's important is that these two functions tend towards 0 as delta x and delta y tends towards 0. So we can take a limit of these two functions as delta x and delta y go to 0 as we get closer and closer to the actual point. And these guys should disappear is the idea, is that in the limit, we end up with literally the total derivative. Okay. So this is the definition of differentiability. And then we have this theorem here on differentiability that makes things a little bit easier for us to understand. So a function f is differentiable if both the x and y partial derivatives exist and are continuous in an open ball. Remember, just some fattening around a and b of size epsilon maybe. So if these both exist and are continuous in this open ball, then f is differentiable. So the are continuous is really important here. Later on, we'll see an example of a function f where the partial derivatives both exist at the point, or at a point AB, but the function will not even be continuous there, and so it can't be differentiable there as well. All right, but that's for later, and then we need to finish our objectives and our terms. So the things I want you to know from this section are, I want you to understand and be able to graph sections of functions. You should be able to compute partial derivatives of simpler functions. Sometimes there will be some complicated stuff, but more or less, this is all stuff that you know from Calc 1. The actual computation is not new. All we do is ignore one of the variables when we compute an x or y derivative. All right, the medium objectives, I want you to be able to interpret partial derivatives geometrically. So same as the standard derivative of a single variable function is the slope of a tangent line, the partial derivatives of a function f are the slopes of tangent lines in different directions. So in particular, along the x and y directions. All right, what else? You should be able to compute tangent planes and linear approximations. These are really the same thing. You just use the tangent plane to compute a value to get a linear approximation. And these actually come from being able to compute partial derivatives. What else? You should know the difference between capital delta of z and little delta of z. I explained that just a second ago, but we'll see hopefully some examples of that later on. I think I have one example ready. And last, the hard objectives. Understand multivariable differentiability criteria. Okay, so this is understanding what the open ball is, what it means to get close to a function in a linear way, and sort of match the tangent plane. What it means for a tangent plane to exist in one spot. I have a nice picture of that on the next page, but this is still, I think, a very difficult idea to get behind. Okay, and then our last objective here is to have some intuitive understanding of classic PDEs. So we're only going to do some very, very, very minor exercises with like Laplace's of the wave equation, but having some idea of how these things work and what they mean, what they might be used to model, is a useful skill, especially if you're going into mathematics or any sort of scientific field. All right, let's move on to our next page then. And we'll start looking at pictures, our favorite part, or my favorite part at least. I don't know about you guys. Okay, so the section of a function basically looks like this. And I mentioned that we would see this picture where we've sliced out a piece of the function. So the function is represented by this blue surface here. And then if I fix y equals b and sort of trace out all of my possible x values, then my function traces out this line right here. Similarly, if I fix A and trace out all of my y values in the xy plane, then my function traces out this line right here. And so we take derivatives of these to get partial derivatives, which is the next part. Okay, so here, partial derivatives. We've got a similar blue surface here, a little bit in the back there. And then these sections, I didn't draw the axes in because it was a little too messy. But we have these sections here where the lines are parallel to the x and y axes. Or not parallel, but they have no, the x line has no x component, so it doesn't move closer to or further away from the zx plane, and the y line doesn't move closer to or further away from the yz plane. Right. And so these lines have slopes as though they're in one dimension. Just measure the triangle right there. And those slopes are the partial derivatives at this point, as long as they exist. Okay, so next up we have Laplace's equation. And Laplace's equation comes from this, which I forgot to label. This is Poisson's equation. Okay, so these guys are all French. They did a lot of work in PDEs. But Laplace's equation comes from Poisson's equation, and I've kind of modified this a little bit here. This is not exactly Laplace's equation, and people might get mad at me for saying that. But the idea of Laplace's equation is that it's supposed to be steady state solutions to different sorts of physical phenomena. So you take this Poisson's equation and you wait a really long time, take the limit as t goes to infinity, and if ft goes to 0, then the t component becomes unimportant here, and you are supposed to end up with this steady state solution, which models maybe the concentration of something. Oh, actually, I wrote down what it models. So Laplace's equation is a model for heat conduction, electrostatics, chemical concentrations over a long period of time, gravitation, fluid flow, all sorts of cool stuff. It's just what happens after a long time. Okay. Now, harmonic functions, these are the actual solutions to Laplace's equation. So if you graph a function like this, the colors mean something, they might have an extra component here. Don't worry too much about the colors. The shape of the graph is what we're interested in, that we have this sort of fixed steady state. This is what the concentrations look like after a long time graph here. And here they have a top-down view of it. I think the colors might just be to indicate height. Okay. So harmonic functions are solutions to Laplace's equation. Oh, and I have one more underneath this. I missed that. The wave equation looks like this in 2 dimensions. And it's, of course, a model for wave motion, any sort of oscillating periodic behavior. Examples are ocean waves, light, and sound. So in 1 dimension, you can think maybe like a jump rope going up and down. So the motion actually is up and down. That would be the u part. And then this is the x variable. So you can think about at any time and any position, a point on this jump rope is somewhere in space, and it's either moving down or up. Okay. And so in some cases with like specific boundary values, you fix some information about the endpoints of a region, you can get solutions like this that sort of look like when you wiggle a jump rope at just the right frequency. Okay. Moving on, we have a fun picture here, the tangent plane. Okay, so this is the same picture as before when we had our partial derivatives, except now I've labeled things a little differently and drawn a plane in. So these are still our lines Lx and Ly, except now I've put some vectors in here, ux vector and uy vector, and I've called my surface u instead of f. We still have the point AB. And then this tangent plane here is called T sub AB of U. This is the plane containing those lines Lx and Ly and spanned by these two vectors. Just means contains those two vectors as well. You can get the normal vector by taking the cross product of these two. We can see that here. If these are tangent, then their cross product is tangent to both of them, and thus must be normal to the surface at that point. So it's normal to the tangent plane. And this is the formula for that normal vector. Okay, so the linearization is the exact same thing, but you just think of things a little differently. The tangent plane thought of as a local approximation to U, which just means once you get the tangent plane, if you want to know the value of the function a little bit away from this point AB, maybe you plug in A plus epsilon, B plus delta a little bit away, then if the tangent plane approximation is a good one, the value of the z value of the tangent plane at that same point should not be too different from the value of the function at that point. There might be a slight error, but it should be small if you're close to AB. Okay. What about increments? All right, so here we have a little bit of a different picture. We have this patch of surface here. We have two different points that are a parallelogram away here. So I guess this is a perspective rectangle, not a parallelogram. Although rectangles are parallelograms. Okay. So we have this here where one side is our change in x, delta x, and our change in y. And the values of the function at different points. And then we have the tangent plane here and its value at a point. And for the increment, we're concerned about the difference in the actual function values. So if I draw a curved line on the surface here, then I think maybe going across the parallelogram here. I'm not sure if you can see that. So diagonally across the parallelogram between those 2 points. We trace from here to here and then take the difference of those z values, and that is our increment. It's the actual change in height of the function between these 2 points. All right, so now the differentials and total differential. This is the change in height between the z value over here, the initial z value, and the tangent plane's z value later on. So we still have the surface in mind here, but we're thinking of this now as the z values of this tangent plane. And that's what we're interested in when we write little delta of z. Okay, I've also written this as a dot product over here. This might be helpful if you do vector calculus. Down here, this is kind of important. Little delta of y and little delta of x, these are the exact same numbers as capital delta x and y. They are just written this way to be notationally consistent here. So I'm not writing little delta, capital delta, and getting confused here. And so this is the change in height, tangent plane, this guy, between these 2 points. All right. Last is what is a differentiable function. Okay, so function, again, is differentiable at a point if the tangent plane exists there. I guess exists and is unique is probably important. I'll add that in real quick. And is unique. In mathematics, unique means the only one. Okay, so I can't have 2 different tangent planes. Okay, another way is what we said before. There are these 2 functions, epsilon 1 and 2, so that you can represent the increment in a linear fashion where these guys eventually disappear. All right, and then to understand that a little better, here's a couple of pictures that show what differentiable and not differentiable might look like. So differentiable functions are typically the nice smooth ones that we're familiar with. Not differentiable functions might look like this. Okay, so they're smooth kind of everywhere else, but then at this point right here, we have a corner or a cusp. And so no matter which direction you come at this, you get different tangent planes from different directions. And so there's no unique tangent plane here. There may not even be a tangent plane. Over here, we have an interesting example of a non-differentiable function. So this is one, the one that I mentioned, I have an example of. So we have this function here, and it's got partial derivatives in the x direction and the y direction at this point. Those both exist and they're continuous, but I have two different tangent planes because if I come along this curve, or these curves right here that are at right angles or 45-degree angles to the original lines, I could get a different tangent plane approximation. And so I don't know which of these to use at this point. So the function we say is not differentiable there. In fact, it's not even continuous there because the limit does not exist or does not equal the value of the function no matter where I place it. Okay. All right, so that's it for our overview. And then in the next video, we'll cover some examples of working with partial derivatives.